Let's do some more of section 4.5. We need to get really good at use substitution. That's undoing the chain rule. Again, we're learning our first technique of anti-differentiation, use substitution, which undoes the chain rule. From page 405, section 5.4, we learned some antiderivative rules so far, and they're coming from just going backwards on derivative shortcuts. We know the derivative of sine x is cosine x, so the antiderivative or indefinite integral of cosine x is just sine x plus c. The antiderivative of sine x is negative cosine x plus c. The derivative of natural log x is 1 over x, so the antiderivative of 1 over x is natural log x plus c, etc. Now, if you notice when we looked at these earlier, that we used x instead of u. And in fact, when I said these a minute ago, I used the variable x instead of u. This antiderivative of cosine u du equals sine u plus c says the same thing as antiderivative of cosine x dx equals sine x plus c. It doesn't matter what you call the independent variable. Okay? It's just that the problems usually have x in them. And for example, let's look at this problem, most general antiderivative or indefinite integral of 2x over x squared plus 1 dx. That's really of this form right here. Most general antiderivative of 1 over u du. Really? This antiderivative of 2x over x squared plus 1 dx is really in this form, antiderivative of 1 over u du? Yes, it is, but it's hard to see that. What use substitution does is it reveals the form that a definite integral is in, an indefinite integral, by the way, if the chain rule was used to differentiate. If the chain rule was used to differentiate and they give us that function to anti-differentiate, then use substitution will reveal the original function. I'm stating these rules on page 403 now using u, because when we use use substitution, we're going to get one of these forms, and the variable is going to be u. Okay, let me illustrate. We did a couple of use substitutions yesterday. You've done a couple for homework. If you've done your Dropbox homework, we're just going to do some more practice. I'm going to let u be x squared plus 1. You may say, why did I let u be x squared plus 1? That's not all that obvious here, I realize. Let's just suppose I wanted to let u be x squared plus 1. Let's see what happens. I agree, that's not all that obvious that you should do that. The next step in u substitution is to take the differential of u. Now remember, the differential is the derivative. So that would be 2x plus 0, or 2x, times dx. Again, dx is the differential of the independent variable. Du is the differential of the dependent variable. There's a section in Chapter 4 that's not on our syllabus that tells you what differentials are good for. But we use them in this symbolic process of use substitution. Okay? It's just a step you need to remember. Now, we take this original problem and we rewrite it with u's. So notice in the denominator I have x squared plus 1. But that's just u. Now notice what's left. 2x dx is left. What's 2x dx? That's just du. Now what goes here in the top? It's 1 du. Now I know that I've said this du is just a part of this antiderivative symbol. And it is. And now I realize I'm treating it kind of as its own entity. But I'll repeat, U substitution is a symbolic procedural thing that works. Usually I will tell you the concepts are so important you need to understand why things work and the concepts. Here's a rare case when I'm telling you just follow the procedures. U substitution is a procedure that undoes chain rule. It works every time if the chain rule was used to differentiate. Now, I see the antiderivative of 1 over u du. Look up here. I know that's natural log absolute value of u plus c. But what is u? U is 2x plus 1. U is 2x plus 1. I'm sorry, u is x squared plus 1. So here's my most general antiderivative.